Welcome to the Walton Pi. Today we're going to be talking about what product sigma algebras are and how we're able to figure out what their generating sets might be. So let's start off by defining what is a product sigma algebra. So let's let X alpha, where alpha comes from some indexing set, let's let that be an indexed collection of sets. So then for every alpha, we are going to let M alpha be a sigma algebra on the set X alpha. The product sigma algebra, which we denote with this like big time symbol and an O, so denoted the product over all alphas of M alpha on our set X, which is the product of all of our spaces, X alphas. That is going to be the sigma algebra generated by the set pi alpha inverse of E alphas. Okay, so the pi alpha, that's the projection map. So we're saying, okay, if I start with an E alpha, I'm going to unproject it to the set of all points that would project down into that E alpha. So by taking that, we're getting this sort of like backwards stripe of all the different things. So it's everything that could project down onto being E alpha. That is going to be our set, where pi alpha from X to X alpha is our natural projection or evaluation map. So that's exactly what this is. So how can we figure out what the generating sets for this might be? So we have this nice proposition that tells us a way to be able to figure out some of these sigma algebras in the case where our indexing set is countable. So if our index set is countable, then the product of our M alphas is going to be the sigma algebra generated by this set, where we are able to write this not as just pre-images using the projection map, but actually just products of elements from our different sigma algebras. So we are able to write it as being generated by the set of the product of those E alphas directly. Okay, so note that for a fixed alpha and E alpha in our sigma algebra M alpha, we are able to write the pre-image of E alpha under the projection map as the product over all the betas in our indexing set of y alpha, where y alpha is E alpha if alpha is equal to beta, and x beta if alpha is not equal to beta. Okay, so we're able to write it like that. So then that tells us that the generating set for M alpha is contained in the product of those E alphas. Okay, so this specific product is precisely those things that generate the sigma algebra. So because it's contained in that set, that tells us that by a previous lemma, and I'll have a video on the screen, the product over the M alphas is contained in the sigma algebra generated by this set. So now we have to go the other way. So since our indexing set is countable for E alphas in our M alpha sigma algebras, the product over our alphas of our E alphas, that's the intersection of our pi alpha inverses of E alphas. That's a countable intersection of members of the generating set for that sigma algebra. That tells us that the product over those E alphas is a subset of our sigma algebra, and we have containment in both directions. So that tells us that we are done, and these two sigma algebras generated by different sets are in fact the same sigma algebra. Okay, so now suppose that for each alpha in our index set, M alpha is generated by E alphas. Okay, so the E alphas here, these are elementary families, and so this allows us to be able to deal with something even if the product is over an uncountable set. So our previous lemma was dealing only with countable. This one allows us to deal with an arbitrary collection. However, we do need to have found an elementary family for each of those sigma algebras. Okay, so suppose that for every alpha, M alpha is generated by some elementary family. Then the product of the M alphas is generated by the set of the pre-images of the E alphas, where each E alpha comes from that elementary family, not just our sigma algebra, but comes from our elementary family. Okay, For our forward containment, all we have to do is note that this set that we have written here, that's a subset of the set that actually generates our sigma algebra. So by that same video, or that same proof from the video that I linked on screen, that tells us that the sigma algebra of our elements that originate from our elementary family, that's going to be contained in the sigma algebra generated by everything that we need. And so now we're going to go through and do the reverse direction. Okay, so consider a fixed alpha in our indexing set. Then we can say that Q, where Q is defined to be the set of all subsets of X alpha, where the preimage of P is an element of the sigma algebra generated by just the elementary family, that is going to be a sigma algebra on X alpha. Okay, so now if we have C coming from this sigma algebra, then the preimage of C is an element of the sigma algebra generated by just our elementary family. Okay, so since that is a sigma algebra, we can say that the product over all X alphas minus this set is also going to be an element of the sigma algebra. So that tells us that the preimage of X alpha minus this set C is in that sigma algebra. So X alpha minus C is in our sigma algebra Q, and Q is going to be closed under complements. The case where Q is closed under countable unions is very, very similar. I'm not going to go through it here, but it is very, very similar, and it follows almost the exact same process, just with like some slight tweaks in a couple spots. So now note that E alpha is a subset of the sigma algebra Q. So that tells us that M alpha is a subset of Q, since E alpha is a generating set for M alpha. Then for P in our sigma algebra M alpha, pi inverse of P is an element of our sigma algebra generated by our elementary family. So that tells us that the generating set for the product of M alphas is contained in the sigma algebra generated by just the preimages of our elementary family members. So that tells us that the product of our M alphas is contained in the sigma algebra generated by just these. And so we have containment both directions, so we have equality. Okay, quick corollary. Suppose that for every alpha in our indexing set, M alpha is generated by an elementary family. If A is countable, and for each alpha, X alpha is an element of our elementary family, then the product of our M alphas is generated by just the product of the elementary family members. And the conditions of this theorem allow us to directly use the previous two propositions to reach the conclusion. Go ahead, pause the video, go back, look at those other two propositions, but you are able to use exactly the previous propositions to be able to get the conditions work out perfectly, and everything falls out very, very nicely. I hope this video was helpful. If it was, please like and subscribe. It helps me to keep making these videos. I hope you have a great rest of your day, and good luck with all of your math.